In the cold, dark expanse of our solar system, beyond the asteroid belt, lie the giant planets. Some can be seen with the naked eye, others only glimpsed once by a passing probe. We are again sending cameras to the edge of the solar system to bring us new insights into the evolution of our worlds. Pioneer 10 and 11 made the first passage through the asteroid belt, leading the way for the venerable Voyager missions. These two probes made a grand tour of the outer solar system before slipping away into interstellar space. Jupiter, the first and greatest of the outer planets with its broiling sky, has had fleeting visits from other missions, like Ulysses, Galileo and Cassini, each adding to the mosaic of Jupiter and its violent atmosphere.
My name is Amy Simon Miller, and I study the atmospheres of the Jovian planets. Weather on Jupiter is confined to a rather thin layer, kind of high up in the atmosphere. So the tops of the clouds are what we're seeing when we look at Jupiter. One thing we're seeing in the southern part of the equatorial region is little V-shaped clouds or chevrons, and we wanted to understand how those are moving in the atmosphere.
What we think chevrons are simply holes in the clouds. They are simply areas where we don't see any bright white clouds.
The Cassini mission flew by Jupiter in the year 2000, and because it was a slow, distant flyby, we got a lot of coverage of the planet over a long time period. So we were able to put those images together and make movies.
Using these movies, we observed Rossby waves that caused north-south meanders in a jet stream south of the equator. With new movies, we instead focused on hotspots. Hotspots are unique because we believe that there is a Rossby wave similar to what we previously detected, but instead of this Rossby wave moving north-south, it primarily moves up and down in the atmosphere. The downward portion of the wave pushes air down into warmer layers of the atmosphere. This causes any clouds that are embedded within the wave to evaporate and prevents further clouds from forming. So at any given time, there are approximately 8 to 10 hotspots in Jupiter's atmosphere that are spaced roughly evenly apart from one another. We believe that each of the downward portions of this Rossby wave corresponds to the hotspots that we see on Jupiter. This new finding is exciting because it'll allow us to re-examine the Galileo probe data and allow us to better understand it and better place it in the context of Jupiter's overall global climate and atmosphere.
The latest probe to be specifically aimed for Jupiter is Juno. Launched 2011, the probe will reach Jupiter after a 5-year journey. Juno's goal is to investigate Jupiter's interior structure and magnetosphere and help improve our understanding of the formation of the planet and therefore the history of our solar system.
Juno spins like a propeller, where the propeller's kind of facing the sun because they're all solar powered.
If you spin something, it stays spinning. It's like a gyroscope. We can use a spinning spacecraft to let each instrument get its turn to see Jupiter. We get to go very close to the planet, inside the radiation belts instead of outside the radiation belt. We're in a polar orbit, so by small adjustments of the timing, we can map the entire planet. We can get repeated stripes at different longitudes as Jupiter spins underneath us.
It does mean that Juno is going to see the polar regions to a greater extent than with other spacecraft. But I think the most important thing is that it gets in very close to the planet as part of that ellipse brings it in a few thousand miles above those cloud tops, very close, near the equator.
We're going to go over the poles of Jupiter. That means we can study the magnetosphere in a different way.
A magnetosphere is the sphere of influence of a magnetic field. So a planet that has a magnetic field has a magnetosphere when its sphere of influence extends beyond the planet out into space and affects the region around it. The magnetosphere of Jupiter is vast. So if you think of Jupiter being 10 times the size of the Earth, and the magnetosphere is 100 times the size of Jupiter.
The Juno probe is the furthest NASA has sent a solar-powered spacecraft. Sunlight provides 25 times less energy than on Earth, which means it requires advanced solar power technology with solar cells which are both 50% more efficient and more radiation tolerant than silicon cells. The craft also houses an electronics vault, which is radiation shielded to protect the electronics aboard from the intense and deadly radiation environment around Jupiter. The probe carries a full set of sensors: a microwave radiometer for atmospheric sounding and composition study, plasma and energetic particle detectors, a vector magnetometer, a radioplasma wave experiment and ultraviolet, and an infrared imager, plus a color camera called JunoCam.
In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife and sister goddess of Jupiter. And Jupiter was sort of being naughty with some friends, so he cast a veil of clouds around himself and his friends. But of course, Juno was a fairly powerful god herself and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to. And that's exactly what the Juno spacecraft does for us, is that it goes there with special instruments in a special orbit and uses its powers to see right through Jupiter's clouds and understand its true nature, which is holding these secrets for us about how the solar system formed and where we all came from.
A long-standing feature of the storms of Jupiter is the Great Red Spot. Large enough to swallow the Earth, this storm system has been studied since the 19th century. Then it was measured at a little over 41,000 kilometers on its long axis. Voyager 1 and 2 measured it at over 23,000 kilometers, and recent observations by the Hubble Space Telescope have the red spot at only 16,500 kilometers long. It seems the rate of shrinkage is increasing. One day it will probably vanish altogether. Juno will also help confirm the theory that Jupiter was the first of the planets in the solar system to form from the primordial disk of dust and gas some 4.6 billion years ago.
I would expect Juno to tell us more about how planets work, meaning how the heat gets out, what kinds of flows exist inside the body, how magnetic fields get generated. Learning what Jupiter is made of, we will learn such a wide range of things. For indeed, Jupiter is the most massive planet in the solar system. It is the body you want to understand in order to understand the architecture of everything else, including Earth.
Juno's year-long mission will end with a deorbit burn and a slow descent into the upper atmosphere, where it will continue to send back scientific data until its destruction. Perhaps the jewel of the solar system is Saturn, with her spectacular rings. All four of the outer planets have rings of ice and rock, but Saturn's is the most complicated, and, with thousands of ringlets, the most visible. There are several groups of rings classified A through to G. Some are formed by shepherd moons within the rings, and by gravitational tidal effects from others outside. Yet some gaps are still unexplained. The current spacecraft at Saturn is Cassini on its second extended mission, the Cassini Solstice mission, which is expected to be completed in 2017. It continues to watch the planet-sized storms in the atmosphere.
Great white spots on Saturn are these large storms that erupt about once every year on Saturn. A year on Saturn is 29 Earth years. The great white spot that erupted in December 2010 initially presented itself as a small little white fluffy cloud that came up, and various instruments on Cassini were seeing it, and ground-based instruments seeing it as well. And as the days progressed, the storm got larger, and then it got sheared from the top and the bottom of the storm on either side of it, and it wrapped all the way across the planet. We'd never before been able to study a storm system of this magnitude in the infrared, so we are very fortunate at this time to have a spacecraft in orbit and excellent ground-based facilities, allowing us to make a historical record of this great white spot. And that will allow us to compare it in future generations when the next one happens.
Another phenomenon is a hexagon of clouds around the North Pole of Saturn, which has recently come into the light.
Cassini has been in orbit around Saturn for 9 years, and we've been following this hexagon which surrounds the North Pole. It's bigger than 2 Earths, and it's a wandering jet stream. But it's been winter in the north, so we have not been able to see what's at the center of the hexagon. But now it's spring, and what we found at the center of the hexagon is a Saturn hurricane. This is a view from directly over the North Pole, which is made possible by the orbit of the spacecraft, which is now taking us over the poles. The winds are flowing at 300 miles an hour, which is 4 times hurricane force. The fluffy white clouds in the center are about the size of Texas. We can use special filters to measure the heights of the clouds, and the red are low clouds and the green are high clouds. We call it a Saturn hurricane because it has the eye, it has the high winds, but it's different from an Earth hurricane because it's locked to the North Pole. And unlike a terrestrial hurricane, there's no ocean underneath. And that's one of the puzzles we're trying to figure out.
A phenomenon first observed on Saturn by Pioneer 11 in 1979, and common to Earth as well, are polar auroras. These magnetic-generated light shows are far more spectacular on Saturn, rising hundreds of miles above the planet's poles. And unlike on Earth, where bright displays fizzle after only a few hours, auroras on Saturn can shine for days. Auroras are produced when speeding particles, accelerated by the sun's energy, collide with gases in a planet's atmosphere. The gases fluoresce, emitting flashes of light at different wavelengths. The Hubble Space Telescope has been watching them closely.
starting in 2016, ending in 2017. These orbits will take us up and over the north and south poles of the planet.
We're actually going to dive in between the innermost edge of the D-ring and the upper atmosphere of the planet itself.
From that, we're going to learn how is Saturn constructed from inside out.
We'll also get the magnetic field of the planet, the mass of the rings for the very first time, and get to sample a place that no spacecraft has ever flown before.
This is a mission that cannot be duplicated. So we really want to take advantage of this opportunity to observe seasonal variation in the system.
Uranus has had only one visitor from Earth, Voyager 2. Like the other gas giants, Uranus has a ring system, a magnetosphere, and numerous moons. There the similarities end. Images from Voyager revealed a featureless atmosphere with no cloud patterns or storms. Uranus differs in its orientation as well. Tilted onto its side, its poles lie where other planets have their equators. Its magnetosphere is off-center and tilted as well, generating an unusual asymmetrical field. This causes Uranus's auroras to be well off the poles. Observations from Earth have shown seasonal change and increased weather activity as Uranus approached its equinox in 2007. The wind speeds on Uranus can reach 250 meters a second. Although there are currently no scheduled missions to Uranus, there have been several proposals put forward, both jointly from ESA and NASA and JPL, including both nuclear and solar-powered probes and an atmospheric descent probe. Ion propulsion is favored because it allows a greater mass to be sent to the planet. Ideally, a probe could be launched in 2020 with a 13-year cruise to Uranus. As this is considered a low-priority mission, no funding has yet been allocated. The eighth and last planet in our solar system is Neptune, the last of the gas giants. Made of hydrogen and helium, it has trace amounts of methane, which gives the planet its beautiful blue color. It too has only been visited once by Voyager. The detailed images taken at that time revealed white clouds and a massive storm marring its atmosphere with supersonic winds.
The storm revolves around the planet every 18 hours. And then it rotates around its own axis like a big glob of pizza dough every 16 days.
Voyager also identified a ring system and confirmed 14 moons. Triton is its largest and is believed to have been captured by the planet from the outer Kuiper belt. Voyager also discovered Neptune's magnetic field was off-center and tilted, not unlike Uranus. Both Uranus and Neptune have had very little close-up study, and various missions have been proposed to fill the gap in our understanding of these ice giants. NASA has looked into several possible missions back to Neptune, perhaps a similar probe design to that of Cassini-Huygens, but due to fiscal and other constraints, none have been approved.
The Voyager mission to the outer planets has certainly been a journey of a lifetime. Having encountered Triton as the last world we would visit, I don't see how any of the scientists could have been happier.
Next stop was Pluto. When New Horizons was conceived, built, and launched, Pluto was still a planet. The downgrade to dwarf made little difference to its investigation.
Well, you know, the key to planetary science is that you really have to go places to get the resolution, to get up close enough to really see what's going on. We want to get up close and personal.
New Horizons is the first really of a whole new breed of spacecraft that is focusing on a very specific task.
For this mission, the questions are basic. What do Pluto and Charon look like, and what are they made of?
We had to really be disciplined and say, we can't do everything. Let's focus on the primary questions and design the instruments to answer those primary questions.
New Horizons was built light and launched on a very powerful rocket, breaking all previous speed records when it left Earth on a solar escape trajectory at 16.26 kilometers per second. The spacecraft passed the orbit of the Moon in just 9 hours. It then cruised for just 1 year to reach Jupiter, where it was given a gravity boost, increasing its speed by 2 kilometers per second and cutting the travel time to Pluto by 3 years. New Horizons was the first to visit the dwarf planet and Charon, its largest moon. Pluto failed one of the 3 criteria to remain a fully fledged planet. It has not cleared the neighborhood around its orbit. Pluto is part of the Kuiper belt and not the only dwarf planet residing there. This is an image of Pluto at its closest approach. It still remains a treasure trove of scientific questions and hopefully answers about the origins and evolution of the solar system. From Pluto's flyby, it is on to the unknowns of the Kuiper belt. The most numerous objects in the solar system are the ice dwarf planets that make up this donut-shaped region on the edge of the solar system.
It's kind of like the asteroid belt, but much bigger. It has hundreds of times more objects in it than the asteroid belt.
The spacecraft will visit some of these objects in its travels.
Once you have the orbit, and we know where the spacecraft is and where it's going to be, we can figure out how much fuel the spacecraft is going to need to use to get to these objects.
After some careful calculations,
it looked like we might actually have to burn the engines to miss the object, which was a pretty exciting concept. You know, it's a good thing we looked, because you wouldn't want to run into one of these things.
These cold classicals, they're pretty much as they were 4.5 billion years ago. They're little fossils. That's incredible. We have no idea what they're going to look like.
New Horizons will continue to explore the outer solar system until 2026.